Everything you need to know about digital integrated circuits, digital ICs. Digital integrated circuits, digital ICs, are electronic components that use digital signals and logic gates to perform a wide range of functions, including data processing, storage, and manipulation. Unlike analog ICs, which work with continuous voltage levels, digital ICs operate with discrete binary values, zeros and ones, and are fundamental to the world of digital electronics. Here are the key aspects of digital ICs. Binary logic, often referred to as Boolean logic, is a system of logic used in digital electronics and computer science, which deals with binary variables and binary operations. In binary logic, all values are reduced to two distinct states, typically represented as 0 and 1. These binary values are used to make decisions, perform calculations, and process information in digital systems. Here are the key aspects of binary logic. Binary variables. In binary logic, there are two fundamental binary variables, 0, often representing false or off, and 1, often representing true or on. These values are used to represent the absence or presence of a condition, a logical state, or a signal. Logical operations. Binary logic involves a set of fundamental logical operations or gates that manipulate binary variables. These operations include an operation. The result is 1 only if both inputs are 1. Symbolically, it is represented as A and B, or simply AB. Or operation. The result is 1 if at least one input is 1. Symbolically, it is represented as A or B, or simply A plus B. Not operation. The result is the opposite of the input. Symbolically, it is represented as not A, or simply A. XOR, exclusive OR, operation. The result is 1 if the inputs are different, one is 0 and the other is 1. Symbolically, it is represented as a XOR B. NAND, not AND, operation. The result is the opposite of the AND operation. Symbolically, it is represented as an AND B. NOR, not OR, operation. The result is the opposite of the OR operation. Symbolically, it is represented as a NOR B. XNOR, exclusive NOR, operation. The result is 1 if the inputs are the same, both 0 or both 1. Symbolically, it is represented as a XNOR B. Truth tables. Truth tables are used to define the behavior of logical operations. A truth table shows all possible combinations of input values and their corresponding output values for a specific operation. For example, the truth table for the AND operation is as follows: A, B, A, and B. 0, 0, 0. 0, 1, 0. 1, 0, 0. 1, 1, 1. Logic circuits. Logical operations are implemented using logic gates, which are electronic circuits designed to perform specific logical functions based on the principles of binary logic. Logic gates are the building blocks of digital circuits and are used to create complex logical structures, such as adders, multiplexers, flip-flops, and more. Applications. Binary logic is fundamental to the operation of digital computers, microcontrollers, and digital systems. It is used in a wide range of applications, including arithmetic operations, data storage, control systems, decision-making, and digital signal processing. Boolean algebra. Binary logic is often formalized and expressed using Boolean algebra, a mathematical system that provides a rigorous way to analyze and manipulate binary variables and logical operations. Binary logic forms the foundation of digital electronics, enabling the processing, storage, and transmission of digital data. It plays a crucial role in the design and operation of digital systems and computers, providing the means to represent and manipulate information in a binary format. Logic gates are fundamental building blocks of digital electronic circuits. They perform basic logical functions on binary input values, 0 and 1, and produce binary output values based on well-defined logical rules. These gates are used to construct complex digital systems and are essential in various applications, including digital computers, microcontrollers, and control systems. Here are the most common types of logic gates. AND gate, AND. Function: the AND gate produces an output of 1 only when all of its input signals are 1. It multiplies two binary values. Truth table: A, B, A, and B. 0, 0, 0. 0, 1, 0. 1, 0, 0. 1, 1, 1. OR gate. Function: the OR gate produces an output of 1 when at least one of its input signals is 1. It adds two binary values. Truth table: A, B, A, or B. 0, 0, 0. 0, 1, 1. 1, 0, 1. 1, 1, 1. NOT gate. Function: the NOT gate, also known as an inverter, produces the complement of its input signal. It changes 0 to 1 and 1 to 0. Truth table: A NOT A. 0, 1. 1, 0. NAND gate. Function: the NAND gate is a combination of an AND gate followed by a NOT gate. It produces an output of 0 only when all of its input signals are 1. Truth table: A, B, A, NAND B. 0, 0, 1. 0, 1, 1. 1, 0, 1. 1, 1, 0. NOR gate. Function: the NOR gate is a combination of an OR gate followed by a NOT gate. It produces an output of 1 when none of its input signals is 1. Truth table: A, B, A, NOR B. 0, 0, 1. 0, 1, 0. 1, 0, 0. 1, 1, 0. XOR gate, exclusive OR. Function: the XOR gate produces an output of 1 when an odd number of its input signals is 1. It is often used for tasks like binary addition without carry. Truth table: A, B, A, XOR B. 0, 0, 0. 0, 1, 1. 1, 0, 1. 1, 1, 0. XNOR gate, exclusive NOR. Function: the XNOR gate is the complement of the XOR gate. It produces an output of 1 when an even number of its input signals is 1. Truth table: A, B, A, XNOR B. 0, 0, 1. 0, 1, 0. 1, 0, 0. 1, 1, 1. These basic logic gates can be combined to create more complex logic circuits that perform various logical and arithmetic operations. Digital systems are built by connecting these gates in specific configurations to perform specific tasks, such as data processing, memory storage, control, and decision-making. Combinational logic is a fundamental concept in digital electronics that refers to a type of digital circuit or system in which the output is solely determined by the current combination of inputs and is not influenced by previous inputs or the circuit state. Combinational logic circuits are designed to perform specific logical or arithmetic operations and are often composed of various logic gates. Here are the key aspects of combinational logic. Stateless operation. Combinational logic circuits are stateless, meaning they don't have memory elements or feedback loops. The output depends only on the current input values, and it changes immediately when the inputs change. Boolean algebra. Combinational logic circuits are often designed using Boolean algebra, a mathematical framework for expressing and manipulating binary values, 0 and 1, and logical operations, and, or, not, etc. Boolean expressions are used to describe the behavior of combinational logic circuits. Basic building blocks. Combinational logic circuits are typically built using basic logic gates, such as AND, OR, NOT, XOR, NAND, NOR, and XNOR gates. These gates are used to implement various logical and arithmetic functions. Truth tables. Truth tables are used to define the behavior of combinational logic circuits. A truth table lists all possible combinations of input values and their corresponding output values for a specific circuit or logic function. Applications. Combinational logic is used in various applications, including arithmetic operations, addition, subtraction, multiplication, and division. Logical operations, AND, OR, NOT, XOR, etc. Data encoding and decoding. Multiplexing and demultiplexing. Code conversion, binary to gray code, BCD to binary, etc. Data comparison, equality and inequality testing. Data routing, selecting data from multiple sources. Data transformation, conversion of data from one format to another. Block diagrams, combinational logic circuits can be represented using block diagrams, where blocks represent different logic functions or gates, and arrows indicate the flow of data from inputs to outputs. Carnot maps, K-maps, are graphical tools used to simplify and optimize combinational logic circuits. They help minimize the number of logic gates required to implement a specific function. Design and analysis. The design of combinational logic circuits involves selecting the appropriate logic gates and creating logical expressions that describe the desired functionality. Circuit analysis is used to ensure that the circuit meets the specified requirements. Multiplexer and demultiplexer, multiplexers, mux, and demultiplexers, demux, are common examples of combinational logic circuits. Multiplexers select one of several input lines and route it to an output, while demultiplexers distribute a single input to one of several output lines based on control signals. Decoder and encoder. Decoders are used to select one of several output lines based on a binary input code, while encoders convert an input into a binary code. Combinational logic is essential in the design of digital systems, providing the foundation for data manipulation, decision-making, and arithmetic operations in digital electronics, including microprocessors, memory systems, and control units. Understanding combinational logic is crucial for digital circuit designers and engineers working with digital systems. Sequential logic is a fundamental concept in digital electronics that deals with circuits and systems where the output depends not only on the current inputs but also on the past inputs and the state of the circuit. These circuits incorporate memory elements, typically flip-flops or latches, to store information and enable sequential behavior. Here are the key aspects of sequential logic. Memory elements. The fundamental building blocks of sequential logic circuits are memory elements. The most commonly used memory elements are flip-flops and latches. These components store binary information, 0 or 1, and can hold this information over time. The state of the memory elements at any given time is often referred to as the state of the sequential circuit. Clock signals. Sequential logic circuits are often controlled by a clock signal, which provides timing for the operation of the circuit. The clock signal determines when the memory elements should read and store data, and when the stored data should be updated. State diagrams. To design and understand sequential circuits, engineers often use state diagrams, which visually represent the different states of the circuit and the transitions between these states. State diagrams help describe the behavior and functionality of the circuit. State tables. State tables are used to define the behavior of sequential circuits in tabular form. They describe the present state, next state, inputs, and outputs, indicating how the circuit should transition from one state to another. Sequential logic elements. Some key sequential logic elements and concepts include flip-flops. These are bistable devices that can store one bit of information. Different types of flip-flops include D flip-flops, JK flip-flops, and T flip-flops. Latches. Latches are similar to flip-flops but can change their state based on the inputs at any time, whereas flip-flops change state based on the clock signal. Registers. Registers are used to store multiple bits of data and are often used for data storage and data manipulation in microprocessors. Counters. Counters are sequential circuits that counter sequence through a series of states based on clock inputs. Shift registers. Shift registers are used to shift data from one location to another in a serial or parallel fashion. Synchronous versus asynchronous logic. Sequential logic can be classified into two main categories based on clock signals. Synchronous logic. In synchronous logic, the operation of memory elements and the transitions between states are controlled by a clock signal. This approach ensures that all components operate in a coordinated manner. Asynchronous logic. In asynchronous logic, there is no global clock signal, and transitions between states can occur independently of a central clock. This approach can be more complex to design and analyze. Applications. Sequential logic is used in various applications, including microprocessors, memory systems, control units, state machines, data storage, and complex digital systems where temporal sequencing and memory are essential. Understanding sequential logic is crucial for designing digital systems that need to maintain state, perform timing-sensitive operations, and execute a sequence of tasks. Sequential circuits are a fundamental part of modern digital electronics, including computers, microcontrollers, and embedded systems. Registers and memory are two essential components in digital systems and computers, serving as storage elements for data and instructions. While they both provide storage, they serve distinct purposes and have different characteristics. Here's an overview of registers and memory. Registers. Purpose. Registers are small, high-speed storage elements within the CPU, central processing unit, of a computer. They are used for temporary storage of data and instructions during the execution of instructions by the CPU. Size. Registers are typically small, with sizes measured in bits. Common register sizes include 8-bit, 16-bit, 32-bit, and 64-bit registers. The size of a register determines the maximum amount of data it can hold. Speed. Registers are the fastest storage elements in a computer. They can be accessed in a single clock cycle, making them ideal for high-speed data manipulation during CPU operations. Functionality. Different types of registers serve specific purposes. General-purpose registers, used for a wide range of data manipulation tasks, such as arithmetic, logic operations, and data movement. Program counter. PC stores the memory address of the next instruction to be executed. Stack pointer. SP keeps track of the top of the stack in a computer's memory. Instruction register. IR holds the current instruction being executed. Memory address register. MAR contains the memory address of data to be read from or written to in memory. Memory buffer register. MBR temporarily stores data being read from or written to memory. Accessibility. Registers are internal to the CPU and are directly accessible by the CPU. They are used for fast, short-term data storage. Memory. Purpose as memory, also known as RAM, random access memory, serves as a large and relatively slower storage system for data and instructions in a computer. It holds data and instructions that are actively being processed by the CPU. Size. Memory is much larger than registers and is typically measured in megabytes, MB, or gigabytes, GB, in modern computers. The size of memory determines the total amount of data and programs that can be stored and accessed. Speed. While memory is faster than storage devices like hard drives or SSDs, it is significantly slower than registers. Accessing data from memory typically takes several clock cycles. Functionality. Memory stores both data and program instructions that are required for the operation of the computer. It can be read from and written to by the CPU. Accessibility. Memory is external to the CPU and is accessed via the memory bus. Data and instructions are fetched from memory and loaded into registers for processing by the CPU. Registers serve as a buffer between memory and the CPU, allowing for faster data manipulation. Types of memory. Computers often include different types of memory, such as main memory, RAM. This is where active programs and data are stored while the computer is running. Cache memory, a small, high-speed memory located between the CPU and main memory, used to store frequently accessed data to speed up processing. Read-only memory, ROM, a type of memory that contains firmware or instructions that are permanently stored and not modified during regular operation. Virtual memory, a technique that uses a portion of the hard drive as an extension of RAM to compensate for insufficient physical memory. Registers and memory work together to enable the operation of a computer. Data and instructions are transferred between memory and registers, with registers providing high-speed data manipulation capabilities, while memory provides the bulk storage capacity required for running applications and storing data. Counter and shift register ICs, integrated circuits, are specialized electronic components used for counting and shifting digital signals. These ICs are commonly used in various applications, including digital data processing, signal synchronization, and control systems. Here's an overview of counter and shift register ICs. Counter ICs. Counting function. Counter ICs are designed to count the number of input events or clock pulses and provide an output that represents the count. They can be used to implement various counting operations in digital systems. Types of counters. There are different types of counter ICs, including up counters. These increment the count for each input pulse. Down counters. These decrement the count for each input pulse. Bidirectional counters. These can count both up and down based on control signals. Decade counters. These are designed to count in decimal, 0 to 9, and reset to 0 after reaching 9. Binary counters. These count in binary and can have various modulus values. Applications. Counter ICs are used in applications like frequency measurement, event counting, digital clocks, timers, and pulse generation. Synchronous versus asynchronous counters. Counter ICs can be either synchronous or asynchronous. Synchronous counters use a common clock signal for all flip-flops, ensuring that they change states simultaneously, while asynchronous counters can change states independently. Shift register ICs. Shifting function. Shift register ICs are used to shift data in a serial or parallel fashion. They allow data to be moved from one location to another within a circuit. Serial versus parallel shift registers. Serial shift registers. These shift data bit by bit through the register, often with a single data input and a clock signal. Parallel shift registers. These shift all data simultaneously using multiple data inputs and a common clock signal. Types of shift registers. There are various types of shift registers, including serial in, serial out, SISO, shift registers. Serial in, parallel out, SIPO, shift registers. Parallel in, serial out, PISO, shift registers. Parallel in, parallel out, PIPO, shift registers. Applications. Shift register ICs are used in applications like data storage, data serialization, parallel to serial and serial to parallel conversion, data transfer between different clock domains, LED displays, and delay circuits. Shift register chains. Multiple shift registers can be chained together to create longer shift registers, allowing for more significant data storage and manipulation. Both counter and shift register ICs play crucial roles in digital systems by providing mechanisms for counting events, synchronizing signals, and manipulating data. They are often used in combination with other digital ICs to implement more complex digital functions and data processing tasks. Microcontrollers and microprocessors are key components of digital and embedded systems, but they serve different roles and have distinct characteristics. Here's an overview of each. Microcontrollers. Definition: a microcontroller, MCU, is a compact integrated circuit that contains a CPU, central processing unit, memory, and various peripherals, all on a single chip. It is designed for embedded systems and is optimized for controlling specific tasks. On-chip components. Microcontrollers typically include a CPU core for executing instructions, program memory, flash or ROM, for storing the program code, data memory, RAM, for temporary data storage, input-output, I/O, pins to connect to external devices, peripherals like timers, UART, PWM, and ADC for interfacing with the external world. Often a clock oscillator and reset circuitry. Low power. Microcontrollers are usually designed to be power efficient, making them suitable for battery-powered or energy-constrained applications. Real-time operation. MCUs are often used in real-time systems where tasks must be executed with precise timing and control, such as in industrial control systems and robotics. Applications. Microcontrollers are commonly found in a wide range of applications, including embedded systems in appliances and consumer electronics, automotive control systems, engine control units, airbag systems, IoT devices and sensors, medical devices, industrial automation and robotics, home automation, Programming microcontrollers often involves writing firmware in languages like C or assembly language. The code is typically loaded onto the MCU's program memory. Example manufacturers. Leading manufacturers of microcontrollers include Microchip Technology, PIC series, Atmel, AVR series, and ST Microelectronics, STM32 series. Microprocessors. Definition: a microprocessor, MPU, is the central unit of a computer system, responsible for executing instructions and managing data. It is typically used in general-purpose computing devices like personal computers. Components: microprocessors include a CPU core. No built-in program memory, ROM, so an external program memory, e.g., RAM or flash, is required to load the operating system and application software. Data memory, RAM, for data storage and processing. Complex instruction set computer, CISC, or reduced instruction set computer, RISC, architecture. Extensive instruction set for general-purpose computing tasks. Multiple input-output I/O pins to connect to external devices via buses like PCI, USB, and SATA. Performance-oriented, microprocessors are designed for high-performance computing, making them suitable for running operating systems and a wide variety of software applications. Applications: microprocessors are used in personal computers, servers, laptops, smartphones, tablets, and many other general-purpose computing devices. They are not typically used in low-power or real-time applications. Programming: microprocessors are programmed using high-level programming languages like C, C++, and assembly language. They run operating systems and a wide range of software applications. Example manufacturers. Leading manufacturers of microprocessors include Intel, AMD, and ARM, used in many mobile devices. In summary, microcontrollers are specialized for specific embedded applications, emphasizing low power consumption and real-time operation, while microprocessors are designed for general-purpose computing and high performance, running operating systems and software applications. The choice between the two depends on the specific requirements of the application. Logic families are a classification of integrated circuits, ICs, based on the underlying technology and electrical characteristics they use to perform digital logic functions. Each logic family has its own set of features, advantages, and limitations, making them suitable for different applications. Some common logic families include TTL, transistor logic. Developed by Texas Instruments in the 1960s. Uses bipolar junction transistors. Offers high noise immunity and fast switching speeds. Commonly used in early digital applications and microcontrollers. Requires a 5V power supply. CMOS, complementary metal oxide semiconductor. Uses complementary pairs of metal oxide semiconductor, MOS, transistors. Offers low power consumption, making it suitable for battery-operated devices. Common in modern microcontrollers, processors, and digital circuits. Compatible with a wide range of voltage levels. ECL, emitter-coupled logic. Uses bipolar transistors in a differential amplifier configuration. Known for high-speed operation and low propagation delay. Consumes significant power, primarily used in high-speed applications like telecommunications and signal processing. RTL, resistor transistor logic. One of the earliest logic families, now largely obsolete. Based on discrete resistors and transistors. Slow and inefficient compared to modern logic families. DCTL, direct coupled transistor logic. A variation of RTL that introduced direct coupling between transistors. Improved speed and power characteristics compared to RTL. HTL, high threshold logic. Uses higher voltage thresholds for logic levels, enhancing noise immunity. Historically used in noisy industrial environments. ECL, emitter-coupled logic. Uses bipolar transistors in a differential amplifier configuration. Known for high-speed operation and low propagation delay. Consumes significant power, primarily used in high-speed applications like telecommunications and signal processing. GTL, Gunning Transceiver Logic. Designed for high-speed data transfer between chips on a circuit board. Uses a low-voltage differential signaling (LVDS) approach. Suitable for high-speed buses and inter-chip communication. BiCMOS, bipolar CMOS. Combines features of bipolar and CMOS technologies. Offers the speed of bipolar transistors and low power consumption of CMOS. Used in high-speed, mixed-signal applications. LVMOS, low-voltage CMOS. A subset of CMOS, designed to operate at lower voltage levels. Commonly used in modern microcontrollers and digital devices. HCMOS, high-speed CMOS. A subset of CMOS, optimized for high-speed operation. Used in applications that require a balance between speed and power consumption. AC, advanced CMOS. A family of CMOS devices optimized for high performance, power efficiency, or other specific requirements. The choice of a logic family depends on factors like power consumption, speed requirements, noise immunity, and voltage compatibility. Each logic family has its advantages and disadvantages, and selecting the appropriate family is crucial in the design of digital circuits and systems. Modern digital electronics predominantly use CMOS logic due to its low power consumption and versatility. ASICs, application-specific integrated circuits, and FPGAs, field programmable gate arrays, are both types of digital integrated circuits used for different purposes in the world of electronics. Here's an overview of each and how they differ. ASIC, application-specific integrated circuit. Customization. ASICs are custom-designed integrated circuits created for specific applications. They are highly customized to perform a particular set of functions or tasks. Design process. Designing ASICs involves a complex and lengthy process. It typically includes detailed hardware description, logic synthesis, and fabrication at a semiconductor manufacturing facility, foundry. Performance. ASICs offer high performance and efficiency for their intended purpose since they are optimized for specific tasks. Power efficiency. ASICs are often power efficient because they are designed with the specific power requirements of their intended application in mind. Non-programmable. ASICs are not programmable after fabrication. Their functionality is fixed, and any changes or updates require a new design and fabrication. Cost. Designing and manufacturing ASICs can be expensive, especially for low-volume or one-off applications. Applications. ASICs are used in a wide range of applications, including specialized microcontrollers, custom processors, application-specific signal processing, and hardware acceleration for tasks like cryptography. FPGA, Field Programmable Gate Array. Customization. FPGAs are programmable integrated circuits that can be customized by the user or designer to perform a wide range of digital functions. They can be reconfigured as needed. Design process. Designing for FPGAs is typically faster and less costly than designing ASICs. It involves creating a hardware description in a hardware description language, HDL, and configuring the FPGA to implement the desired logic. Performance. FPGAs offer a balance between flexibility and performance. While they are not as optimized as ASICs for specific tasks, they can be highly efficient for various applications. Power efficiency. FPGAs can be power efficient if configured to perform tasks efficiently, but they may consume more power than custom-designed ASICs for the same application. Programmable. FPGAs are highly programmable and reconfigurable, allowing users to modify their functionality as needed. Cost. FPGAs are generally more cost-effective for low to medium production volumes or when design changes are anticipated. Applications. FPGAs are used in various applications, including digital signal processing, rapid prototyping, development and testing of new digital systems, software-defined radios, and hardware acceleration for tasks like image and video processing. In summary, ASICs are designed for specific, high-volume applications where performance and power efficiency are critical, and the cost of development can be justified. FPGAs, on the other hand, offer flexibility and reconfigurability, making them suitable for applications with changing requirements, rapid prototyping, and low to medium production volumes. The choice between ASICs and FPGAs depends on the specific needs of the application, development time, cost considerations, and the required level of customization. Clock and timing integrated circuits, ICs, are specialized electronic components used to generate, distribute, and manage timing signals in various electronic systems. These ICs play a critical role in synchronizing and coordinating the operation of digital devices, ensuring that different components work together efficiently. Here are the key aspects of clock and timing ICs. Clock generation. These ICs are designed to generate clock signals with specific frequencies and characteristics. Clock signals are essential for timing the operation of digital circuits, processors, and other components within a system. Clock distribution. Some clock and timing ICs are used to distribute clock signals to various parts of a system. Clock distribution is crucial to ensure that all components operate in sync and maintain the correct timing relationships. Frequency synthesis. Clock ICs can generate clock signals at various frequencies by dividing or multiplying the input frequency. This flexibility is valuable in applications that require different clock speeds for different components. Clock jitter reduction. Clock jitter refers to variations in the timing of clock signals. Some clock and timing ICs are designed to reduce jitter, ensuring that signals are stable and accurate. Phase-locked loops, PLLs. PLL ICs are used to synchronize the phase and frequency of an output signal with a reference input signal. They are commonly used in applications such as radio frequency, RF, communication and data transmission. Real-time clocks, RTCs. RTC ICs are used to keep track of time, date, and calendar functions. They are commonly found in devices like watches, clocks, and various consumer electronics. Crystal oscillators. These ICs are often used as the timing source for many clock and timing applications. They rely on the vibration of a crystal to produce a highly accurate and stable clock signal. Clock buffers. Clock buffer ICs are used to isolate and strengthen clock signals, ensuring that they maintain their integrity as they are distributed to different parts of a system. Delay lines. Delay line ICs are used to introduce controlled delays in signals, which can be useful for synchronization and alignment in various applications. Applications. Clock and timing ICs are used in a wide range of applications, including microprocessors, communication systems, data storage devices, networking equipment, test and measurement instruments, and more. Frequency control. Some clock and timing ICs offer control features, allowing users to adjust and fine-tune the frequency and timing characteristics to meet specific requirements. Synchronization. In applications where multiple devices need to work together, clock and timing ICs ensure that data is transmitted and received at the correct time, reducing data errors and enhancing system efficiency. GPS disciplined oscillators. These ICs use signals from GPS satellites to discipline an oscillator, providing an extremely precise and stable clock source. Clock and timing ICs are critical components in modern electronic systems, ensuring that digital devices can communicate, process data, and function in a coordinated and synchronized manner. Selecting the right clock and timing ICs is essential for the reliable operation of complex digital systems. Multiplexers, MUX, and demultiplexers, DeMUX, often referred to as MUX and DeMUX, are digital logic devices used in various applications to route and distribute data or signals. They play a crucial role in data selection, transmission, and distribution in digital systems. Here's an overview of multiplexers and demultiplexers. Multiplexers, MUX. Function. Multiplexers are used to combine multiple input signals into a single output. They are commonly used to select one of several input lines and route it to the output based on control inputs. Input selection. MUXs have multiple data inputs, usually 2 to the power of n inputs, and a set of select lines that determine which input is routed to the output. The number of select lines determines the number of input lines that can be accommodated. Applications. MUXs are used in a wide range of applications, including data transmission, signal routing, data acquisition, and communication systems. Multiplexing ratio. The multiplexing ratio of a MUX is the number of input lines divided by the number of select lines. For example, a 4:1 MUX combines 4 input lines into 1 output with 2 select lines. Example, 4:1 MUX. Inputs, A, B, C, D. Select lines, S0, S1 2 select lines to choose one of the 4 inputs. Output, Y. The selected input is routed to the output based on the select lines. Demultiplexers, DMUX. Function, demultiplexers perform the reverse function of multiplexers. They take a single input and distribute it to one of several output lines based on control inputs. Output selection, DMUXs have multiple output lines and a set of select lines that determine which output line receives the input data. Applications, DMUXs are used in various applications, including data demultiplexing, signal routing, and data distribution. Demultiplexing ratio. The demultiplexing ratio of a DMUX is the number of output lines divided by the number of select lines. For example, a 1:4 DMUX takes one input and routes it to one of 4 output lines with 2 select lines. Example, 1:4 DMUX. Input, X. The input signal to be distributed. Select lines, S0, S1 2 select lines determine which output line receives the input signal. Outputs, Y0, Y1, Y2, Y3. The input is routed to one of the 4 output lines based on the select lines. Multiplexers and demultiplexers are essential components in digital systems and data communication networks. They are often used to manage data transmission and reception, enabling efficient routing and distribution of digital signals and data. These devices are crucial for tasks like data multiplexing, demultiplexing, time division multiplexing, and signal switching in various applications, including telecommunications, data acquisition, and control systems. Digital signal processors, DSPs, are specialized microprocessors designed to efficiently process and manipulate digital signals in real time. They are used in a wide range of applications where fast and efficient signal processing is required. Here are the key features and applications of DSPs. Key features of DSPs. Efficient signal processing. DSPs are optimized for mathematical and logical operations commonly found in digital signal processing, such as filtering, convolution, correlation, and complex arithmetic. Fixed point or floating point arithmetic. DSPs can be designed to perform fixed point or floating point arithmetic, depending on the specific application requirements. Fixed point DSPs are often used for cost-sensitive applications, while floating point DSPs offer higher precision at the cost of increased complexity. Parallel processing. Many DSPs feature multiple processing cores or execution units, allowing them to perform multiple calculations simultaneously, which is crucial for real-time processing. Hardware accelerators. DSPs often include hardware accelerators such as multiply accumulate (MAC) units, designed to perform common DSP operations efficiently. High clock speeds. DSPs typically operate at high clock speeds, enabling them to process signals in real time. Specialized instruction set. DSPs come with specialized instruction sets tailored for signal processing tasks, which can significantly enhance processing speed. Efficient memory access. DSPs are designed to efficiently access memory, with features like circular buffering to process continuous data streams. Applications of DSPs. Audio processing. DSPs are commonly used in audio systems for tasks like audio compression, e.g., MP3, noise reduction, equalization, and audio effects, reverb, echo. Telecommunications. DSPs are used in modems, codecs, and baseband processing for tasks like data modulation, error correction, and channel equalization in wired and wireless communication systems. Image and video processing. DSPs are used in digital cameras, image sensors, and video codecs to process and enhance images and video, as well as for image compression, JPEG, and video compression, H.264, MPEG. Radar and sonar systems. DSPs are employed in radar and sonar systems to process signals for target detection, range finding, and signal filtering. Medical imaging. DSPs are used in medical imaging equipment, such as MRI and CT scanners, for image reconstruction, filtering, and enhancement. Automotive DSPs are found in vehicle systems for tasks like engine control, audio processing, advanced driver assistance systems, ADAS, and infotainment systems. Consumer electronics DSPs are used in various consumer products, including smartphones, gaming consoles, and smart TVs, for audio and video processing. Aerospace and defense DSPs are used in military and aerospace applications, including electronic warfare, radar, and signal intelligence. Industrial automation DSPs are employed in control systems for tasks like motor control, robotics, and process automation. Scientific and research instruments DSPs are used in laboratory and research equipment for data acquisition, signal analysis, and experimental control. DSPs have become essential in the modern world due to their ability to process real-time signals efficiently. They continue to advance in terms of performance and power efficiency, enabling a wide range of applications in various industries. Digital signal processors DSPs find application in a wide range of fields where real-time signal processing and data manipulation are essential. Here are some prominent application areas of DSPs. Audio processing. Audio effects and mixing in music production. Noise reduction and echo cancellation in telecommunications. Audio compression and decompression, e.g., MP3 encoding/decoding. Telecommunications. Modems and codecs for data transmission and voice communication. Wireless and cellular communication systems. Digital filtering and channel equalization for signal integrity. Image and video processing. Image enhancement, color correction, and denoising in digital cameras. Video codecs for compression and streaming, e.g., H.264. Image and video analysis in surveillance and security systems. Radar and sonar systems. Signal processing for target detection and tracking. Range finding and Doppler processing. Beamforming for directional signal reception. Medical imaging. Image reconstruction and enhancement in MRI and CT scanners. Signal processing in ultrasound imaging. Biosignal analysis, e.g., ECG and EEG, for diagnosis. Automotive electronics. Engine control units, ECUs, for fuel injection and performance optimization. Advanced driver assistance systems, ADAS, for collision avoidance. Infotainment systems with audio and video processing. Consumer electronics. Smartphones for image and audio processing. Gaming consoles for real-time graphics rendering and audio effects. Smart TVs for image and audio enhancement. Aerospace and defense. Electronic warfare systems for signal intelligence and countermeasures. Radar and sonar applications for target detection. Communication systems for secure data transmission. Industrial automation. Motor control for robotics and manufacturing equipment. Process control and monitoring in industrial plants. Data acquisition and analysis for quality control. Scientific and research instruments. Laboratory equipment for data acquisition and signal analysis. Control systems in experimental setups. Spectroscopy and imaging in research applications. IoT, Internet of Things. Sensors and edge devices for data collection and pre-processing. Edge computing for real-time analysis and response. Data communication and connectivity in IoT networks. Embedded systems. Microcontrollers and microprocessors in various embedded applications. DSPs in automotive, consumer electronics, and industrial control systems. Environmental monitoring. Weather prediction and climate modeling. Air quality monitoring and pollution control. Earthquake and seismic signal processing. DSPs are vital in these application areas due to their ability to perform real-time signal processing tasks efficiently. They play a significant role in enhancing the performance, accuracy, and functionality of systems across a wide spectrum of industries.